Assalamu alaikum. My name is Muhammad Arif Aziz, and today we are going to talk about torsion of a circular shaft. Torque. Torque is a moment T, which is T is a representation of a torque that tends to twist a member about its longitudinal axis. The torque action is also known as torsion. Let us consider a circular shaft before and after deformation, as shown in the figure. See, this is a circular shaft which is before deformation. So we apply the torque on the either side. See, we apply the torque here and torque here. After the application of torque, as shown in the figure, when the T is applied at the shaft, the radial lines will remain straight. So where are the radial lines? This is the radial lines. It will remain straight. The circular cross section remains circular. The circular cross section remains circular, but the longitudinal line become twisted. This is the longitudinal lines. This is the original position. Suppose this is straight from here to here. Now it is twisted from here to here. This is the situation after deformation. Torque is a moment that twists a member about its longitudinal axis. If the angle of rotation is small, the length of shaft and its radius will remain unchanged. This is just an example of a typical example of a torsion failure in the wood member. The formula of torsion can be represented by the following equation. Torsion formula is the formula for the shear stress tau developed in a shaft subjected to a torque. So this is tau max is equals to Tc over J, where tau max, it's over, right? It's tau max. Where tau max, the maximum shear stress in the shaft which occur at the outer surface. T is the resultant internal torque acting at the cross-sectional area. Its value is determined from the method of section and the equation of moment equilibrium applied when the shaft longitudinal axis. This is T torque, which can be determined by the method section method or equation of equilibrium. J, the polar moment of inertia of the cross-sectional area, and C is the outer radius of the shaft. C is the outer radius of the shaft. For polar moment of inertia for solid and hollow circular object are, for solid circular, it is J is equals to pi by 2 C raised to the power 4, where C is internal or outer radius of the shaft. C is the radius raised to the power 4. And for the hollow circular shaft, J is equals to, which is polar moment of inertia, J is equals to pi by 2 C naught power 4 minus C initial power 4 internal. This is outer radius, this is internal radius. Okay, C is representation of radius, J is polar moment, and rest to the power 4. Start with the problem number 1. The solid 30 millimeter diameter shaft is used to transmit the torque applied to the gauge as shown above. Determine the absolute maximum shear stress in the shaft. We have to determine maximum shear stress, that is torque max. This is a circular shaft which having a torque on different positions. We have a position A, B, C, and D. So the length between A and C is 300, C and D is 400, and D and B is 500. So this is the length, and torque is applied, that is 300 anti-clockwise, 500 clockwise, 200 Newton meter clockwise, and 400 Newton meter anti-clockwise. Now we have to determine the C first. What is mean by C? C is the radius. So in this, the solid 30 millimeter diameter bar. So diameter is given. So diameter divided by 2 is the radius. So CAC, CCD, C dB will be same, which is C is equal to diameter over 2, which is 15 mm. Now, this is a solid circular shaft. So the formula for J is pi by 2 C की power 4. This formula. We use this formula, huh? So it is pi by 2, 15 power 4, which is 79.5215 to 10 power 3. So our required is tau, and we have to calculate T now, because in the formula, if you remember, this is the formula. So C is given, C is calculated, J is calculated, T is missing. So to determine the shear stress. So we have to calculate T now. To calculate the T, we have internal torque of the different segment. We have to cut the segments. So moment about A is equal to 0. So we cut the section here. So 300, which is anticlockwise, plus TAC. We assume TAC anticlockwise as well. So we say 300 plus TAC is equal to 300 Newton meter. So our assumption is reverse. Then we cut the section from here to here. We cut the section between here. First section before point C. Now cutting the section before point D. So we will assume this one as well. So the equation will be, the situation will be like this. This is a free body diagram. In the exam, you have to make it like this. That A anticlockwise, C clockwise, and assume any direction of TCD. So we assume anticlockwise. So this is 300, this is 500, and this is TCD. Now making the equation from this, so equation will be like this: 300 minus 500 plus TCD. So TCD will be 200 Newton meter. So it means our assumption is correct. It is TCD is anticlockwise. Now we cut the third section from before this point. Before this point, we cut the section. So our figure will be A, C, D, which is 200, and TDB. Now we will calculate moment at point this. So it will be 300 minus 500 minus 200 plus TBD is equals to 400 Newton meter. So we calculate TAC, TCD, and TDB. Now we calculate the tau max at each point. Okay. Now what is the formula of tau max? Tau max is equals to T times C upon J. So we have tau max for AC. So we will use TAC, CAC, and JAC. Fortunately, CAC and JAC are same for all. So we have to put always TAC, only tau is different. So for the above formula, they modified it like this: C, TAC. So C is remains same for all, and J is remains same for all. Okay. So J is remains same. Only difference in tau value. So for tau AC, we calculate 300, 200, and 400. So it is 300, 200, and 400. We put the value, we got the answer of tau max Newton per millimeter square. So maximum of tau max is AC, like maximum of tau max AC, tau max CD, and tau max BD is 75.45. So which is our absolute answer. Start with the problem number 2. The shaft is supported by 2 bearings and it is subjected to 3 torque. Determine the shear stress developed at point A and B located at the section AA of the shaft. So there is a one you can say there is one two bearings. One, there is one bearing and two bearing, and there is a shaft subjected by three torque. 1, 2, and 3. And there is a section AA. In section AA, we have 2 points, that is A and B. We have to determine shear stress at that point. Okay. So for that circular shaft, the radius of the shaft is 75 mm. So we can calculate polar moment of inertia from this 75. But at point B, the C will be 15 mm. So we will calculate C, and we will calculate C for section point A and C for point B. To determine tau or shear stress, what we have to do, we have to have T C over J. This is our formula. We have to have this one. For J, we need C, and which is given. Now, from the free body diagram of the left segment, we will cut the section at section AA. Summation of moment at x equals to 0. 4250 minus 3000 minus t is equals to 0. In this way, we can determine the t, that is 1250 kilonewton millimeter. The polar moment of inertia of the shaft is J is equals to pi by 2 c to the power 4. This is 4.97 into 10 raised to the power 7 millimeter to power 4. This is wrong. Millimeter power 4. Since point A is at C, rho is equals to C is equals to 75 mm. So we say that torque at A, this is torque at A, is equals to TC over J, which is 1250 into 75 divided by 4.97 into 10 to the power 7, 1.89 megapascal. This is at point A. Then at point B, T into C upon J will be 1250 is T. C here is 15, it is given, and 4.97 into that 10 to the power 7 is a J. So 0.377 megapascal is a shear stress at point B. For the tau, the unit is megapascal, which means Newton per millimeter square. How does it work? See, this is tau, okay, 1250. This is in kilonewton millimeter, and multiply by C. C is the radius, which is in millimeter. It will be millimeter square. So it will be kilonewton millimeter square divided by millimeter power 4. Okay. So it will be millimeter square. So it will be kilonewton per millimeter square. So Newton per millimeter square will be megapascal, and this answer will be this term will be multiplied with 1000 as well. So let me check with the calculator. So if we calculate that, the answer will be 3.77 by multiplying it by multiplying this term into 1000. So it will be in Newton per millimeter square, which is megapascal. So conversion of the unit should be keep in mind. So start with the problem number 3. A shaft is made of steel alloy having an allowable shear stress of T allowable 84 megapascal. If the diameter of the shaft is 37.5 mm, determine the maximum torque T that can be transferred. First of all, we have to make our data that what is given. What is given? Okay. So first thing is given, tau allowable 84 megapascal. Diameter of the shaft is 37. Diameter is given 37.5 millimeter. Okay. Now determine the maximum torque T. So this is our required. We determine the maximum torque T that can be transmitted. Now this is the first case. This is the first case when we have a circular shaft which is solid. Okay, this is solid circular shaft. This is case number 1. This is case number 1. In the case number 2, what would be the maximum torque T dash? In the second one, we have to determine T dash if 25 millimeter dia hole is bored through the shaft. So there is a new hole. This is a circular shaft, but it is hollow. So new hole is bored. This one. This is a new hole. And diameter here in this one, initially it was 37.5, and then from here to here it will be 25, okay, millimeter. Sketch the stress strain distribution along a radial line in each case. Okay, so this is our required. This is a case number 2. This is a case number 1. In the case number 1, T is required. In the case number 2, tau dash is required. Also, we have to determine what is the maximum allowable shear here at that point. Okay, and sketch the shear stress distributed along a radial line in each case. Okay, so let me solve this. Now, first of all, we have to calculate allowable shear. Allowable shear for the case number 1. What is the formula of T allowable? Allowable shear is equal to TC over J. In this case, we have to determine case number 1 T torque, because T allowable is given, which is 84 megapascal. T allowable equals to, okay. Now, what is C? C is given, C is calculated by diameter. Diameter is given 37.5 millimeter. Okay, so C will be D by 2. 37.5 divided by 2 is equals to 18.75 millimeter. So C is 18.75 millimeter. Now J. What is J? For the solid circular shaft, J is equals to pi by 2 C power 4. So it will be pi by 2 into 18.75 power 4. When we calculate, it will give you the answer. Let me calculate. Pi by 2 into 18.75 power 4. It will be 194,144.4 millimeter power 4. This is our J. Okay. We can calculate in this way, or we can put it in the formula directly. It's up to you. Okay. Now, T allowable is 84 is equals to T into C, which is 18.75 divided by 194,144.4. Okay. So to determine T, we can say that 84 multiplied by 194,144.4 divided by 18.75 is equals to T. And it will be multiplied by 84 divided by 18.75. It will be 869,767.10. And what is the unit? Newton millimeter. So to convert into kilonewton meter or any other unit, we can keep it like this. If you want to convert into kilonewton meter, so multiply by 1000 square. So 869,767.1 multiply by 1000. It will be kilonewton multiply by divide by divide by 1000 into 1000. Okay, so it will be kilonewton millimeter. So divide by 1000 to convert into kilonewton to newton, or newton to kilonewton, and from millimeter to millimeter divide by 1000. So it will be 0.8697 kilonewton meter T. Okay. Now, for the unit conversion, how the unit of T is working. Suppose this one. This is 84 megapascal. The unit is here. The unit here for this one is 84 Newton per millimeter square. Okay. And this J, the unit of this J is millimeter power 4 whole divided by 18.75, which is C, and the unit is millimeter. So if we take it from here to here, it will be from the denominator, it will go to the numerator. So it will be cut, and it will be cut, and it will be 1. Like 2 and 1, 3 will be cut, 1 will be there. So it will be Newton millimeter. And then we divide by 1000 into 1000, it will be kilonewton meter. Okay. So this is the first case. We calculate allowable. We calculate T by using the allowable shear. Now I'll erase this. Now for the second case, determine T dash when we have a bore of, see, this is the first case in which we have a diameter of 37.5 mm. Now in the second case, we have a hollow shaft in which the diameter of the hollow shaft is 25 mm. Okay. Now we have to calculate T dash here. For the T dash, we will use the same formula. T allowable is equals to T C over J. Okay. In this case, we will use it. J is equals to, for the hollow shaft, pi by 2 C outer power 4 minus C internal power 4. Okay. So C outer is 37.5 divided by 2 is equals to 18.75 millimeter. It is C outer, and C internal will be 25 divided by 2, 12.5. Why? Because it is diameter. We use C as a radius. So it is J, and allowable is 84. T is tau. C is 18.75. I'm putting the values in this formula. Divided by pi by 2, 18.75 power 4 minus 12.5 power 4. When we solve this, we got T dash is equals to 697961 Newton milliliter, and is equals to 6.698 kilonewton meter. Okay, we can calculate it by the formula. Then sketch it as they ask. Okay. To sketch it, we have solid circular shaft. In this one, our allowable tau is 84 megapascal. Okay, this is allowable 84 megapascal. For the second case, we have a circular shaft. In this one, we have 84 megapascal T allowable. But for this one, this is when T allowable, when T is when C is equals to 18.75. Now we have T dash till this point due to circular shaft. We have to know T allowable till this point. T allowable till this point. So here we use this formula, but rather than using 18.75, we will use 12.5 here. The whole formula will be same, but we will use here as 12.5, and then we calculate allowable by using this T dash. See, T allowable is equals to T dash C upon J. Okay, T dash is, we calculated 0.698 into 12.5 divided by pi by 2, 18.75 power 4 minus 12.5 power 4. The answer by solving this, you got 56 T allowable megapascal. So this is T allowable at this point due to the radius of 37.5 or diameter of 37.5, and this is until this point due to the radius of 12.5 or diameter of 25. Okay, but this is the end of the problem number 3. Problem number 4. The copper pipe has an outer diameter of 40 mm. C outer diameter, D outer is equals to 40 mm, and an inner diameter of 37 mm. If it is tightly secured to the wall at point A, if it is tightly secured at point A to the wall, the 3 torques are applied at it as is shown in the figure. Determine the maximum shear stress developed in the pipe. We have to determine maximum shear stress developed in the pipe. So first of all, we need to cut the section from here. So we cut the first section here and we calculate 80 and Newton meter for first point. Then we cut the section here. Then we calculate 60 Newton meter and then cut section here. We got 90 Newton meter. Okay. So this is easy. I'll show you how to calculate. Suppose this is, if this is clockwise, we assume is anti-clockwise. So anti-clockwise T minus 80 is equals to 0. So T is equals to 80 for this section. For section 2, if it is 80 is clockwise, minus 80, and this is anti-clockwise, plus 20, and we assume this one as anti-clockwise, so it is plus T is equals to 0. So it will be T is equals to 60 Newton meter. And for the third problem, for the third section, it will be minus 80, plus 20, and plus 30. Minus 30. Okay, it's clockwise. It is clockwise actually. Minus 30 and plus T is equals to 0. So it will be 80 minus 20 plus 20, it will be 90. Minus 90, T plus T is equals to 0. T is equals to 90. So out of them, 90 is greater. So we assume T max torsion, maximum torsion as 90. Because we calculate torsion on different section. So that maximum torsion in this one is T is equals to 90 Newton meter. Okay. Now, what is C? C is a radius. The diameter of the shaft is given, I think. Inner diameter is 37 mm and outer is 40 mm. Okay. So outer diameter is 40 and inner is 37. So outer is 40. So outer radius will be 20 because it is 40. D is 40 and D is 37. So inner will be 37 but divided by 2, which is 18.5 millimeter. Okay. And formula of the J is here, pi by 2, outer minus inner. Now they put the value in meter and divide by 1000. So 90 Newton meter. That's why they convert the unit, because 90 is in Newton meter. So 90 Newton meter, what is the formula of 90? Newton meter multiply by, this one is in meter, millimeter to meter, then divided by, this is millimeter power 4. So it will be meter cut, it will be Newton per meter square. When your answer come in this way, they will convert definitely into Newton per millimeter square by multiplying by 1000 square. Let me check and give you the confirm. So actually, when they solve this values in terms of Newton per meter square, the answer will be like this. I calculated it. It is 267331688.34 Newton per meter square. Newton per meter square. So to convert into Newton per millimeter square, divide by 1000 square. So your answer will be 26.7 megapascal, which is Newton per millimeter square. The unit conversion is very compulsory. Like we have to keep everything in your mind while solving the problem. So this is your tau max in the shaft. Problem number 5. The assembly consists of two galvanized steel pipes connected together using a reducing coupling at B. This is a reducing coupling at B. Two galvanized pipes connected with the, where is it? This is coupling B. Okay. Steel pipe connected together using a reducing coupling. This is two steel pipe, 1 and 2. The smaller pipe has an outer diameter of 18.75. The smaller pipe have outer diameter of 18.75 and the inner diameter of 17 mm. So the pipe A consists of outer diameter 18.75, inner is 17. Whereas the larger pipe has an outer diameter of 25 and inner diameter of 21.5. This one have inner and outer diameter as well. If the pipe is tightly secured to the wall at C, determine the maximum shear stress developed in each section of the pipe when the coupling shown in applied the handles of the wrench. This is a coupling shown. Now, for this one, we cut the section TAB and then TBC. Because there is no torque throughout, so TAB and TBC have a torque due to this force only. So for this force, what is the moment? Force. What is the moment or torque? Force times distance. Okay. So in this one, 75 is the force, which is in Newton, multiplied by distance, which is 200 plus 150. Sorry. It is 200 plus 150. When we multiply it, our answer will be 75 into 350, 26250. 26250 Newton millimeter divided by 1000. It will be 26.25 Newton meter. 26.25 Newton meter. So tau at AB and torque at BC will be remain same because we have only one torque. This is, suppose if we cut the section here, torque AB will be 26.25, and when we cut the section here, torque BC will be BCS. It will be 26.25 as well. Okay. Now, what is the formula of allowable shear? Tau is equals to TC over J, where J is internal polar moment of inertia. Sorry, J is polar moment of inertia, and C is the diameter. Okay, C is the radius. So C is given. How we calculate C? I'll let you know. And how we calculate J? For J, the formula is simple. For the J, pi by 2 C outer 4 minus C internal 4. This is the formula for J. And how much is the diameter given for the shaft? 18.75 outer dia for the pipe A. So it is for the pipe A, it is 18.75 divided by 2 is equals to C, which is 18.75 divided by 2, 9.375 C. And for this one, C will be how much? 25 outer dia. So 25 divided by 2, it will be 12.5. So now this is outer dia, so we consider as C. Internal dia, we will put it here. So we have everything. We have T, we have C, and we have pi by 2, this J formula. This is outer diameter and this is inner diameter. So we get the value 62.5 megapascal. And for this one, from where this 8.5 come? This 8.5 is C. 18.75 and 17 mm. So 17 divided by 2 will be 8.5. And this is 21.5 inner diameter. So inner diameter divided by 2 will be inner radius of this object. So 18.9 and 60.2.5 megapascal is the value of torque or shear stress at point AB. Shear stress at point BC is 18.9. Okay, this is the values. So thank you and see you in the next lecture.